Okay, welcome to the 22nd class meeting of the spectrally correlated random processes. First, I want to make correction to the equation shown in the last class meeting, where in this line, where we have orthonormal eigenvector decomposition, here I use the lambda sub I, but it should be changed to lambda sub I of f, because at each frequency f in the Nyquist zone, we have different eigenvalues depending on frequency f. So we need to change it. Anyway, today I'm going to cover the PDF I just uploaded before the class meeting. So you need to download and read it while I presenting today's class meeting. So the title is Translation Series Representation of a Cyclostationary Random Process. And most of the contents of this document is about the zero mean proper complex Y-sense cyclostationary random process. However, as I briefly written at the end of the document, this approach can be generalized with some difficulty, frankly speaking, generalized to the improper, zero mean improper SOCS case. The reason why I'm emphasizing that the assumption of zero meanness is that, as you've seen in the third exam, when you have non-zero mean for second order cyclostationary random process, your mean path has Dirac deltas located at the integer multiples of 1 over capital T. And that makes huge trouble when you use fresh vectorizer or properizing fresh vectorizer, because the fresh vectorizer is an p-fresh vectorizer employ ideal low-pass filter that covers the entire Nyquist zone, especially in the case of the improper case, p-fresh vectorizer. It covers only half of the Nyquist zone, where inclusion or exclusion or half exclusion of f equals 0 is not clear. So we have a big trouble. However, as you can easily see, for the fresh vectorizer, it could be okay. But because your center frequency can be chosen to include the interval of integer multiple of 1 over t with some non-zero measure. So in proper case, there is no problem. But in order to make discussion simple, I'm going to assume that we are handling zero mean complex random processes. So let's start from a review of what we've seen. So from the paper of 2004, we start from this model where D sub n is a zero mean proper complex Y-sense stationary symbol sequence. So it's a random process. And P is a deterministic pulse with bandwidth B. So in general, P of T needs not to be a real valued one. So P of F is in general complex valued, and it does not need to have symmetry at all. So this choice of B, bandwidth, is our convenience, so that if we have a passband signal with asymmetrical spectrum, then we somehow choose F sub C that translates to the origin in this case, and we have B. So you may regard this 2B as the bandwidth in the passband of our real valued bandpass signal of interest. Ready? Now, given this model, what was our result? And what was actually not specifically explicitly shown, but as I explained in the previous class meetings, our trick is to use what? Fresh vectorizer. So fresh vectorizer requires two parameters. First one is the bandwidth of the input signal. So B information is required. And second, in order to choose the Nyquist zone for our bandpass filter, we need to specify the bandwidth, twice the bandwidth of the ideal low-pass filter. So this fresh vectorizer consists of many modulators with oscillator frequencies 1/t apart. And we have a bank of ideal low-pass filters with pass band on the Nyquist zone. Then we have a vectorized version of this random process X. In particular, when we have this model of digitally modulated, linearly modulated PAM or probably QAM signal, we have what? This vectorized Fourier transform is nothing but this vector valued signal. One good thing is that now P of T consists of what? Band limited signals. Band limited to the Nyquist zone. Got it? And for convenience, let's say this P of T has two L plus one components. And we may choose L in this way. Then what was the property of the vector valued signal? This vector valued signal becomes what? Vector Ysen stationary random process. So we may consider autocorrelation function. And we can show that this is a function only of the time difference. So let's define a single variable matrix valued function named the same as the autocorrelation function, capital R sub X vector X vector. Now, let's define tau equals T minus S and then compute the matrix valued power spectral density as a function of F. Then what was our result in the paper 2004? It didn't explicitly say, but we had this one. Here, lambda of F is the scaled power spectral density of the data sequence. Be careful about this F times capital T. Got it? And then we have vectorized Fourier transform of the symbol waveform P, which is simply the entry by entry Fourier transform of this fresh vectorized output of P of T. Got it? And from this result, we have the idea that whenever we have a vector valued Ysen stationary, zero mean of course, complex random process in this form, we may find corresponding signal like this. Got it? The problem is that existence is kind of obvious because we already have derived that result from this model. What about the uniqueness? Can we uniquely recover, not this one, that one, this figure? And here comes the difficulty and subtlety. Why is it so? And it is explained here. Where? Yeah. So let me write it down here. So this can be rewritten as some lambda hat of f, p hat of f, p hat of f Hermitian, where lambda hat is also chosen non-negative. By the way, this is the eigenvalue from the EVD. So we have lambda sub I, the negative for f, we choose. And what you want is that this is true. Or maybe we may put some arbitrary phase. Got it? Because this phase can be cancelled when we perform the Hermitian transposition. Got it? So we can scale P of f vector arbitrarily. One of the simplest choice would be choosing normalized eigenvector here and normalized eigenvector here. So this becomes the eigenvalue. The problem is that it's not required. You may even just let this lambda of f equals 1 for f as far as this is always positive. And we may scale the eigenvector as we wish. So there is no unique assignment of P of f. That's the problem. However, let's still pursue. One good thing is that if we choose lambda of f equals 1, or if we can choose like this, then what happens? This is going to be interpreted as the power spectral density scaled in the f domain. And if it is 1, what does that mean? The data symbol sequence is assumed uncorrelated symbols. So we don't know from the two-dimensional or matrix-valued power spectral density whether our digitally modulated signal, suppose we are going to crack that, we don't know whether the coloredness of the power throughout the Nyquist frequencies, the frequency on the Nyquist zone, we don't know whether the data was originally colored data sequence or uncorrelated, which means white data sequence. We can never know. Right? So that's the problem of the uniqueness. So we have phase ambiguity and we have scale ambiguity. Got it? So just a second. Yeah, I believe everything's well written. Now, from this spectral characterization of a digitally modulated signal, we have translation series representation of arbitrary zero mean proper complex cyclostation random process with cycle period t. Let's see what can we do. So suppose we already have some capital X of t, and suppose we know the cycle period. So we use, ideally, not practically, we use the fresh vectorizer to have x underline vector. Then we have what, as I already told you, we have a matrix valued power spectral density because it's zero mean Y-sense stationary vector random process. Now we apply eigenvalue decomposition to this matrix. Then what will happen? Be careful. This F can be any number on the Nyquist zone. You may remove, include negative 102T and exclude positive 102T. It doesn't matter, okay? As far as there is no point mass there. Okay, since we assume zero mean, no point mass, no problem. Now, what is the property of this matrix? It is Hermitian symmetrical, as stated here, and positive semi-definite. You can show that. Then the story becomes very simple. We apply eigenvalue decomposition for each matrix. Why do I say that? Since F is in the continuum, we have uncountably infinite number of such matrices. So for each F, we have possibly different eigenvalue decomposition. And that is written in this form. So we have here M is the maximum number of non-zero eigenvalues over the entire frequency F in the Nyquist zone. So for example, at F equals 0, you have non-zero eigenvalues, two non-zero eigenvalues. At F equals 1 over 40, you have 3. And then you take the max of it, and max exists. And because it's an integer, right? So you set M. Then for each F, what? You have M's eigenvalue and M's possibly normalized eigenvector, right? So you have also normal eigen decomposition, like this, for each F, and for each F, right? Sum of lambda hat sub M's could be 0, depending on what F you have. And of course, as I told you already, you have phase and scale ambiguity like this. So you may find some other non-negative lambda sub M of F and scaled version or phase rotated version of P sub M of F. We don't know, but mathematically, these two are the same functions. Got it? Now, from our lessons, what we can guess is like this. What if we claim that each summand has its corresponding digitally modulated signal with Y-sense stationary data symbols? By the way, here we are going to assume that different streams, now let me use that term stream, capital different M streams are zero mean uncorrelated, because data sequences are uncorrelated sequences, sequence by sequence uncorrelated, whether each sequence could be colored random process, or that random process could also be consisting of uncorrelated symbols, because we choose corresponding lambda sub M of F as flat one. Okay. It depends on our choice. So what do we have? We have corresponding vectorized version first, right? So we may have some colored random process, or we may have some white random process for the data sequence. It depends on your choice. Uncountably infinite number of choices you have. Now, we are going to use Fresh scalarizer, which is defined as the inverse transform of the Fresh vectorizer. Scalarizer. Then what do we have? We have scalar valued random process. And if you read 2004 paper, not 2004 paper, the Byung-Khan and Jurojo paper about the cyclic water filling, then we prove that if this is vector-wise and stationary, inverse transform is cyclostationary random process with cycle period T is kind of obvious, but anyway, there is a proof. So eventually, we have what? We have capital M, zero mean uncorrelated cyclostationary random processes in the form of what? In the form of digitally modulated signal. Got it? So is it clear now? So I already covered the non-uniqueness of this X of T, non-uniqueness of translation series representation. Now let's see some relation with the KL expansion. So in KL expansion, what did we have? So we have X of T defined on the finite time interval. And now here in translation series representation of zero mean proper blah, 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 what did we have? We have power spectral density that contains all the information about the second order moment of the vector random process restricted to a finite interval. Okay. And what did we do? Here, using Mercer's theorem, we decompose the autocorrelation function of the band time limited random process as what? In this way. So we apply eigen decomposition. What do we do here? Okay, I'd better not say this. Okay, sorry about that. This is more precise. Okay, so let's start from the time domain random process. Okay, so here in translation series using the fresh vectorizer, we converted X of T into a vector value signal X of T, and each component of this vector value signal is band limited. Okay? That is the key actually, not just the Y sense stationarity. And here, what you do is that we decompose the matrix valued power spectral density this way. Do you see the similarity? Ready? This is kind of time limited, scalar valued scalar valued time limited random process. And here we have vector valued band limited Wisen stationary process. This is not necessarily Wisen stationary, but time limited. This is Wisen stationary and band limited. Got it? And eventually, what do we claim? The claim is that the KL expansion says we have the decomposition like this. X of t, which is time limited, is the weighted sum of the eigenvectors, which is time limited. And the scale is done by uncorrelated random variables. Got it? So we assume proper complex. Okay. And here, what do we have? Got it? So here we have a kind of periodicity, cyclostationarity, right? So P of t is periodically transmitted. And we have maximum capital M streams. Of course, you can extend this KL expansion to a vector valued random process. So you may be able to do this. But still, nothing much changing. The key is that this KL expansion, we usually know, has the most important assumption of time limitedness. Whether it's stationary or not, it doesn't matter. For this translation series representation of Wisen cyclostationary random process, we have band limitedness related to the cycle period, because we are using fresh vectorizer to develop this idea. Got it? Anyway, so you see the similarity and difference. This technique, such a technique is quite often used. So from the beginning, you have no idea whether you have some nice representation of random process or not. But as this kind of pseudo proof says, given a zero mean proper complex Wisen cyclostationary random process, you can always find multi-stream type representation, multi-stream digitally modulated signal representation. Unfortunately, it's not unique. And here, the same actually. In the complex case, you have phase ambiguity, right? You have whether this x sub I can be scaled or not. You have no idea, right? Same thing happens here. So there is a kind of very noticeable similarity or commonality between these two techniques. Now, in terms of shift invariant subspaces, what is our result? Our result says that the random process is kind of in the shift invariant subspace with how many? Capital M generators, generating functions. So we have P1 of t up to P sub m of t, which serves as generators of this random process. Of course, as I told you, this shift invariant subspace, the notion is related to deterministic signals, especially finite energy deterministic signals. But any signal in that subspace can be written as a weighted sum of this capital M signals and their t times integer multiple shifted versions. Got it? So you see that the translation series representation of a cyclostationary random process is closely related to shift invariant subspaces with multiple generator functions. Got it? Now, the final comment is on the zero mean improper complex second order cyclostationary random processes. So it's like Fermat, even though I had enough space to write down, I didn't have enough time to fill up the section 5. So let me tell you the sketch of it. So x of t is now assumed as improper zero mean, improper complex second order cyclostationary random process with cycle period capital T. So what do? Here we put properizing fresh vectorizer. Then what happens to x of t? We have a vector valued zero mean, surprise, surprise, proper complex, second order stationary, or if you want Ysen stationary, vector random process with strictly band limited components. Right? So there is no difference between zero mean proper complex Ysen cyclostationary random processes translation series representation and improper case because we have the powerful properizing fresh vectorizer. Actually, the kind of guru in cyclostationarity, the professor, the Dr. Gardner, didn't use this notion of fresh vectorizer, but from the beginning, they knew how to prove the first part. They implicitly, if you read, I cannot claim that I was the first person to have the idea of using that stationarization and proper stationarization of Ysen proper complex cyclostationary random process. They kind of implicitly used to claim that translation series representation was possible. So I cannot get any credit except that I have now consistent way of proof, not only for zero mean proper case, but also for zero mean improper case. Because at this point, everything becomes the same. So since we have proper complex stationary random process here, what do we have? this matrix valued power spectral density can be decomposed into some capital M components. Same, nothing different. Be careful here. F is only what? From 0 to 1 over 2t, half the Nike string, right? By definition of the properizing vectorizer, fresh vectorizer. Got it? Anyway, we can do that for such process. And what do? We may claim that x of t has what? Has some signal like this. Then what happens? This is what? This is zero mean, proper complex, Poisson stationary vector random process, right? So this D is what? This D is a zero mean proper complex sequence. Now, what do we have? Here we have P-fresh scalarizer that converts this signal, vector valued random process, to x of t. What kind of operation do we have in the P-fresh scalarizer? As you remember, we have two branches, right? And then each modulates the components and sum up. But before we add up, we have conjugation operation. And what's the function of this conjugation operation? Anybody? So now, as an example, let's consider some D sub n sequence, which is QPSK. So we have in-phase component and real component and imaginary component. And we have its conjugation. So if we assume that they are uncorrelated, half and half probability, one negative one, then this is proper, right? Now, what is the conjugation? And if we add them up, what do we have? We have improper BPSK signal. So the properizing fresh scalarizer actually is kind of misleading, right? We'd better say that inverse p-fresh vectorization. But anyway, it turns the proper sequence into improper sequence. Got it? So in this way, we can recycle all the arguments on the translation series representation. The only difference is that given improper, zero mean improper complex cyclostationary random process, we have improper complex Ysen stationary kind of data sequences or weighting sequences that kind of is multiplied by the translated version of the deterministic generator functions. Got it? And also, you may see some ideas like this. See that? Suppose you have P1 of t as the generating function of this model, and you have some P. Then what happens in the fresh vectorizer? You have upper part of it, you have a lower part of it, and you take upper part for the upper group branches in the scalarizer, and this part goes to the lower part of the scalarizer and scaled. The problem is that you have what? The conjugation of it. So after you combine them, what happens? You may have the summation of these two as the kind of new generator, and plus and minus, I don't know, I'm not sure exactly, but I believe so. Yeah, so you have some, this part scalarized, that part scalarized version, this one scalarized version, that part scalarized versions, some and possibly difference, probably only sums, but anyway. So you have a different set of generators. That's just as straightforward as the previous proper case. Got it? But still, the scalarized version of these pulses will give you a deterministic signal, right? So that could serve as your generator function. Got it? So I believe I covered very, very fast and covered most of the important results of today's class meeting. Sorry about the technical problem related to our audio system. And thanks to this document, you may find a lot of missing links in my presentation. So read the document carefully and remember what I told you during the class meeting. Then you may easily or without much difficulty, you may understand this translation series representation of a cyclostationary random process. Okay. So it seems we are almost done with this translation series representation. But before we move to the papers, let me give you some interesting twist related to the translation series representation of a discrete time Ysen cyclostationary random process. So for a discrete time Ysen stationary random process, we have something interesting like this. Suppose we have x of n, that is, for simplicity, zero mean proper complex Ysen cyclostationary with cycle period n. Okay, n is an integer. We definitely assume n is greater than 1. Otherwise, it would be y-sense stationary, right? Now, x of n can be converted to a vector-valued random process exactly in the same way as the fresh vectorizer. But that is too simple. What we are going to do is that we have so-called serial to parallel converter. What does that mean? If we collect m of the, n, with parameter n, what does that mean? From some reference times 0, here we have a vector-valued random process that has something like this. So the first vector consists of capital N consecutive elements of the random process. Then what? Then we have next N of them, and so on, right? So in this way, we can define a new vector-valued random process, X, right? So we don't need modulation, we don't need ideal low-pass filtering to vectorize. And you may say that, hey, we just vectorized, what's the use of it? And you can easily show that this vector-valued random process is actually y-sense stationary. We cannot find a straightforward parallelism in the continuous time case. Because in continuous time case, we don't have discrete time indices. We have time index that is from continuum. But for discrete time, we have what? Discrete, countably infinite number of discrete time indices. And rearranging the random process in this way, actually, you can immediately obtain y-sense stationary vector random process. And this operation actually is what? Is related to multi-rate signal processing. So when I presented my result in an international conference, one of the audience raised the hand and asked me whether I have found the link between my result for continuous time case and this multi-rate signal process. He said that your result looks very similar to what I have seen in multi-rate signal process, where he converted the input signal to a vector random process by using simple serial to parallel converter, and then process. And then even he said that he could do some eigen analysis based signal estimation or detection. And then if it was an estimation problem, then again use the parallel to serial converter to get the same rate signal as input signal. So it's nothing but the multi-rate signal processing, he said. And I said, okay, I'll try to find. And I've seen actually from one of the Dr. Giannakis' old paper about discrete time cyclostationary signal processing. Anyway, so you will see something similar to our result. And also the Gardner's paper, I gave you the one of the old paper. that has some idea, similar, very similar comment like this. Okay, so what is the main theme then? What is the main theme common to all these tricks? And what I believe is that the so-called stationarization. Of non-stationary random process. In our case, cyclostationary random process, right? As far as you can find some method to stationarize, to make it stationary, then every analysis is done using our standard mathematical tools developed for electrical engineering. What I have added was what? Properization. On this properization part for improper cyclostationary random process, there were not many ideas at that time. And the papers I wrote with my former graduate students were kind of combining these two. So many of the titles had this second order cyclostationarity and impropriety in the titles. Now, so you understand why I am kind of obsessed in teaching this course. Okay, that's all for today.